What I would like to do now is to take a few minutes and look at a particular type of wave, and that is sound waves. Sound waves, well, I won't tell you what kind they are. Let's see if we can figure that out. Let's imagine that we have a tube here with a diaphragm over at this end. And this diaphragm is maybe connected to a speaker or something like that, so that this thing can move in and out. The speaker on the front of the diaphragm on the front of the speaker can move in and out. What will happen when it starts moving like that? Well, when it moves to the right, in here, what's in here? Well, air is in here. And we've got air molecules throughout this whole tube that roughly have the same density throughout the entire tube. Okay, roughly the same density. What happens, and there's a whole lot more though, right? In real life, there'd be a whole lot more particles in here. When the diaphragm moves to the right, what happens? Well, it compresses the air in front of it. So we end up with a higher density of air molecules in front of the diaphragm when it pushes in. It pushes all the air together and makes a more compressed region of air in front of it. What happens? Well, just like with the masses on a spring, those push on the molecules in front of that, these push on the molecules in front of that, which push on the molecules in front of that. And then when the diaphragm moves the other way and goes back to the left, it makes a region of lower density. So what happens? We end up with these regions of higher density and then lower density, higher density, lower density, which kind of keep pushing on the molecules in front of them, or drawing them in, so to speak, so that we end up with these regions of high density and then lower density. I'll make it lower even still, but erase some of these. And then higher density and lower density. And higher density and lower density. Like this. Okay? And when those things go out of the tube, or they get sent out into the room, and these waves then come and hit your ear, these regions of high density and low density make your eardrum go back and forth. It's connected to the three inner bones of the inner ear, and et cetera, et cetera. You experience it as sound. So this is how sound is made, by having something that is vibrating in the air. Or not just vibrating. I mean, you can have a very sharp sound like that, but the bottom line is something that is moving air, making high density regions and low density regions that we then experience as sound. We could graph this in terms of the density of the air relative to the average air density. The wavelength is then the distance between these two maximum regions of high compression. And everything we've been talking about waves then applies. What I'd like to do is demonstrate some sound waves, not just my voice, which I'm sure you've heard enough of, but I'd like to demonstrate some harmonic sound waves, and hear what differences they have. Just slightly off screen here, I have a signal generator. And what this is going to do is create a sinusoidal variation in voltage coming out attached to these wires, and then these wires are attached to a speaker. And I basically have a speaker right here, and I can change the frequency and the amplitude excuse me, of the variation in voltage. So when we have a positive voltage, actually I'm not sure exactly how, depending on how I put these in here, let's just say a positive voltage will push the speaker forward, a negative voltage pulls it back. So as we vary the frequency or the wavelength of the signal, this is going to push this plunger in and out and in and out, and it's attached to a diaphragm, a speaker diaphragm right in here, and we'll be able to hear it as a sound wave. Right now I have it set at 1 hertz, and I'm going to turn up the amplitude, and hopefully you can see excuse me, that the plunger is going in and out 1, 2, 3, 4 at a frequency of 1 hertz, one cycle per second. I'll turn this up to 2 hertz, 1, 2, 3, 4, 5, 6, So we've got it oscillating at 2 seconds. Now, we can't really hear it. I mean, there is some, excuse me, there is some scratching, a little resistance in the motion, but we don't hear it as a sound wave. I'll come back to that. I'll turn this up. You can still hear kind of that scratching sound, but not really a sound. Turn it up to 20 hertz. Now, above 20 hertz, we start hearing a hum. And that's actually a sound wave. It's actually creating a sound wave. I'll turn this up more. Excuse me, and we can definitely hear that as a sound. I'll turn the amplitude down a little bit. Point it towards the camera so you can hear it as best as possible. Turn this up higher. And what we notice is, let me turn this down. Higher frequencies we experience as higher pitches, higher pitch of the sound. Now that's not always true for all the frequencies, but within part of our auditory range, we hear an increase in pitch, an increase in frequency as an increase in pitch. Now the perceived pitch has to do with other things as well, but more complicated physiological things. But for us, for right now, that's a good enough approximation to say that the frequency of the oscillation we then perceive as the pitch. Higher the frequency, higher the pitch. Or shorter the wavelength, higher the pitch. So I'll turn this back up. Now I'm not sure if you can see this, but I can definitely feel it. This plunger is still just going in and out and in and out, but it is moving air that we then hear. And I'll turn this up higher. So that is 100 hertz. That is a sound of 100 hertz. This is, I'm going to turn this down because there's a little attachment here that is a little bit loose. So I'm going to take this out. Okay. There we go. It's a little bit better. Now I'm going to increase the frequency again. Okay, that's 100, 200. It's a big jump. 3, 4, 5. Turn that down a little bit. 5, 6, 7, 8, 9. Now I've got to change things around here a little bit. There we go. That's 1,000 hertz. We can go up. Whoops. That's 2,000, 3,000, 4,000, 5, 6. To tell you the truth, I'm not sure if the camera is picking up, if the sound microphone on the camera picks this up. But, so, I think we've covered the important aspect. That the frequency of the sound we perceive, for the most part, within a certain range, as the pitch of the sound. And typically, we can hear, people can hear, from around 20 hertz as a sound, not just that you can experience it, but as a sound through your ears, to 20,000 hertz. Now, that is someone with very, very good hearing. Actually, for me, with this, something above 12,000, I've lost my high-pitched hearing. As people age, they tend to lose some of those high frequencies. Well, I've lost mine years ago. I couldn't hear anything above 12,000 hertz. Under ideal conditions, in an ideal situation, like in a sound room with all external sounds cut off, it's said that some people can hear from 12 hertz to 28,000 hertz. 28,000 hertz. There are sounds outside of this range. Just because we can't hear them doesn't mean that there aren't sounds. I've found some information that maybe this has been updated, but when I found it, I found that elephants could actually hear down to 14 to 16 hertz. And that some whales, could hear down to around 7 hertz. That would be sound waves traveling in water, obviously. And there are also sound waves at wavelengths higher than 20,000. Sorry, let me mention one thing. Just like in the visible spectrum, wavelengths longer or frequencies lower than we can see, the lowest wavelengths that we can see are red light, and wavelengths lower than that, just lower than that, are infrared. And so wavelengths longer or frequencies lower than 20 hertz are called infrasound. While higher frequencies, the highest frequency light we can see is violet light. The next part of the spectrum that's there is ultraviolet, so sound just higher than this is called ultrasound. And you might have heard that term when medically someone might get an ultrasound. They're using sound waves of high frequency that can be used to penetrate into your body and make images of what's going on inside. Maybe someone that's pregnant and has a baby, they can see what the baby looks like using ultrasound. Okay. In terms of these high frequencies, if you've ever seen a dog whistle or something like that, dog whistles make sounds in the ultrasound or high frequency region because dogs can hear higher than we can in general. Also, there are some bats that apparently can hear up to around 100 kilohertz, so around 100,000 hertz. Okay, so even though we can't hear it, there are sounds even outside our range of hearing. Now what I'd like to do is talk about a very, very interesting aspect of sound that you might have experienced. If you've ever stood on the sidewalk or been standing on the sidewalk and heard a car go by, I want you to think about, what does that sound like?